I am Jonas Seng from the AI ML group at TU Darmstadt, and I'm going to present a joint work with Pooja, Prasad, Devendra, Singh, Dhami, Martin Mundt, and Kristian Kersting titled Feathers, Federated Architecture and Hyperparameter Search. Nowadays, data is often distributed across multiple parties or data owners, and those are often not able to share their data to a central server to, for instance, apply some machine learning on that data. Often this is due to privacy concerns, for instance, in the medical or financial domain, but also sometimes even in research. To tackle that issue, federated learning was developed as a novel learning paradigm where instead of sharing the data, the model is shared during learning. So a set of clients learns a model locally for a couple of steps or epochs, sends the model to a central server where the model gets somehow averaged and sent back to the clients in order to synchronize. And this process is repeated until convergence. However, in these scenarios, optimizing architectures and hyperparameters remains a challenging task, and existing approaches do not incorporate the dependency between architectural choices and the choice of other hyperparameters. Also, they do not consider privacy, meaning that an attacker might spoof the network and obtain the architecture, the model weights of a model, and maybe hyperparameters. And it has been shown that from all of these three parameter types, it is possible to extract private information from training data. So how can we efficiently optimize neural architectures and hyperparameters jointly with privacy guarantees and federated learning? For that, we propose Feathers, which applies a differentiable neural architecture search paired with a bandit-based hyperparameter optimization approach, combined with differential privacy in order to protect the private information in the training data. In detail, each client holds weight and a set of architectural parameters and a reward vector, and also model parameters, which are omitted in the following slides. And each client starts to select a promising hyperparameter configuration using an immediate reward scheme, and then optimizes the neural architecture locally for a couple of epochs before sending it to a central server where all the architectural parameters and the reward vectors as well as model parameters get averaged and sent back to the clients in order to synchronize. This procedure is repeated until convergence. To evaluate Feathers, we compare it to darts and FedEx in federated learning environments based on 3 image classification tasks and 1 fraud detection task. All datasets were split evenly across clients with and without label skew as common in federated learning. It can be seen that Feathers beats darts and FedEx in 5 out of 6 cases, showing that the joint optimization of architectures and hyperparameters is indeed beneficial. This holds for settings with label skew, but also without label skew, and in settings with a low number of clients and hundreds of clients, even showing that Feathers also scales well. Looking at privacy, we find that Feathers provides practically usable privacy guarantees. So for instance, a typical value for epsilon is 25, which provides strong enough privacy guarantees to protect private information, but still allow learning. It can also be seen that even under differential privacy, Feathers is scalable because we don't see a significant drop in performance if we scale to hundreds of clients. To conclude, Feathers finds state-of-the-art models, provides practical privacy guarantees, and is scalable.